Hi there. So we are going to take what we were learning in the last lesson when we were calculating the enthalpy change, but we're going to take it now and actually take it to the higher level. Okay. So when I said yesterday that an enthalpy change was a fancy name for an energy change, I'm going to be a wee bit more specific today. What an enthalpy change is that it's a change, an energy change, when it's 1 mole of whatever energy change you're having. So let's start with enthalpy of combustion. That's what we're going to concentrate on today, and we're going to take it to the higher level when we're going to find out the energy released when 1 mole of something is burnt. So the enthalpy of combustion is the energy given out when 1 mole of a substance reacts completely with oxygen, so when it combusts. It's this 1 mole thing that is important, and it's what we are going to be working on today. So here is an equation. This is the combustion of ethane, and as you can see, that equation is shown for 1 mole of ethane being combusted. The delta H value for a combustion reaction is always negative, it's always exothermic, right? And that's what we were talking about yesterday. We talked about if an energy change is one where the chemical reaction loses energy, then it would be negative because it's lost energy. If it's an endothermic reaction, then the chemical reaction is taking energy in, so it's going to be a positive change. But we are not going to have any positive changes for enthalpies of combustion. Now, this is slightly different from National 5 or what we were doing yesterday, and you'll see why. So the way it's different is there's going to be one more extra step, and when I show you that, you'll understand what I mean. So just as we were looking at yesterday, we had this setup here where you have your alcohol burner, or maybe like a Bunsen burner or whatever you're burning, transferring that heat energy that has been released when the combustion reaction happens into the water in the can. Okay, and then obviously because it's losing energy, the water is going to take that energy that's been lost in, and the temperature will go up. What we do need to know is some of the questions might ask is why this calculated enthalpy of combustion, which we're going to look at, could be less than the textbook value. Well, the reason is that you could maybe have an incomplete combustion, so not all the bonds are being broken and made again in the same way as complete combustion. There may be different bonds being formed, and this could have different energies. Or heat energy lost to the surroundings. So we want all our heat that we've lost in the reaction to go into the water. However, this does not always happen. It could go into the air, and especially if this insulation here, if that isn't sufficient enough, or if it's not set up correctly, then you could have potentially a lot more heat loss, and that means your value wouldn't be accurate. So these are just things to watch out for. What we're going to do is we are going to work out one of these examples. Now, the first section is going to be similar to what we did yesterday, the energy produced by burning the ethanol. That is going to be the same. However, when we're going to work out the enthalpy, that is the next step. Okay, so we'll work through it together. So as we were doing yesterday, we are going to use the equation E equals Cm delta T. And remember, there was a few things that we had to remember yesterday. Obviously, if it's 100 centimetres cubed of water, that will be the mass, not this 0.72, because that's a mass of ethanol. That will come into what we're doing next. And also, the temperature change was going to be if you had to do two different values, but this one's quite easy because it's just a 1. So as we did yesterday, C is going to be 4.18. The mass is obviously 100 centimetres cubed, becomes 0.1 kilograms, so that's going to be 0.1, and then our temperature change is 25, okay, because it's going up by 25. So this is going to work out using the calculator to be 10.45 kilojoules. And because it's a combustion reaction and this energy has been released, which means it's lost from the chemical reaction, is going to be negative to denote that that's exothermic. Okay, so that is the first step, exactly the same as what we did yesterday. So if you are not sure how to do this, I would maybe go back and do some more practice on what we did yesterday. If you are happy with this, then let's move on to the next part of this. So keep this energy change here in your head, because we're going to use it for the next thing. So this is now saying we need to work out the enthalpy of combustion. So this is actually the energy change when we've got 1 mole of our ethanol being burnt. Okay, so we have, and for the energy change we just worked out, it was 0.72 grams, but we want it for 1 mole being burnt. So I'm going to show you how to do that. We're going to set it out just the same way we might have done some equations before. So we're going to say that when we burn 0.72, we'd release 10.45 kilojoules. However, we want to work out how much we're going to release when we have 1 mole. Now, the mass of 1 mole of ethanol is 46 grams, and I'm going to show you how to do that just in case you've forgotten. So if we write out ethanol's chemical formula, it's going to be C2H5OH. And then if you use your data booklet to work out the masses of all the atoms, we've got 2 carbon atoms, each at 12 grams. We've got 5 hydrogens, each at 1 gram. We've got 1 oxygen at 16 grams. And we've got another wee hydrogen at 1 gram. And if I added that all up together on the calculator, that's going to come out to be 46 grams. So if you were wondering where I got that mass of 1 mole, that's exactly where I just got that from. So I'm going to go back here and we're going to talk about proportion. Okay, so if I've got 0.72, that gives me 10.45 kilojoules. I want to find out what 46 grams is going to give me. So I could do this way. In maths, when you look at linear scale factors, or like scale factors from like National 5, you basically are going to try and use that here. We are now going up to 46. We were at 0.72. So we could do 46 divided by 0.72 and times that by our 10.45. Okay, so this thing here that I'm going to put in brackets, it's almost like your linear scale factor. You would do that and you would times that by 10.45. When my teacher taught me this at higher, she always told me when you were doing proportion that you could always do new over old times the other side. And that's exactly what I'm doing here. I'm doing new, which is this, divided by old times by the other side. Okay. Another thing you can do, and I'll show you this later, is cross multiplication. I'll give you the 2 different ways just to show you that you've got different ways to do it. So going back to this, you've got 46 divided by 0.72 times by 10.45. I would work this out first and use that to work out the final answer. So when I worked this out in the calculator, it came to be 63.89 times by 10.45, and that worked out to be minus 667.64 kilojoules. Now we need to add something else here. Right. Firstly, I'm going to mention this negative. I missed that out here, but remember it's still exothermic, so that negative has to be there. And this is the next thing here. It's per mole. Okay, so we are now working out as kilojoules per mole. Right, and that per mole just is because it's the energy released when 1 mole is burned, so you add that in as well. So if you're talking about an enthalpy, it's going to be per mole as well. Okay, right, I'm going to show you quickly as well, if I've got space, how to do this cross multiplication thing if you want to try it this way. So what we could do is we could do 0.72 over 46 equals 10.45 over x. And you can work this out for x. So you do x equals, and you can swap these two around. Divided by 0.72. And then to get rid of this 46 here, you could times both sides by 46. So that would give you this. X equals 10.45 times 46. I'm going to move that over slightly. Divided by 0.72. And that would give you the same answer as we'd worked out there, which is minus 667.64 kilojoules per mole. So that just gives you two different ways that you could use to work this out. Obviously both of them are all proportion, it's just how you're setting up is slightly different. Okay. Now my preferred way is to do it the first way, but it's just a case of putting the numbers in the way I've said for either way, depending on which way you want to do it. Okay, we're going to try another one, and here it is just now. We're going to look at 50 mils of water being heated up by 40 degrees Celsius when 0.5 grams of methanol is burned. Okay, so let's start with the easy bit. Okay, it's first asking us to calculate the energy produced by burning the methanol. So we will do that just now. It's not asking for enthalpy, so it's the first step that we have to do. E equals Cm delta T. C is going to be 4.18. Mass is going to be the 50 mils of water. So 50 mils is going to turn into, that's the same as 50 centimetres cubed. So that is going to turn into 0.05 kilograms, because you divide it by 1,000. So that's going to be 0.05 times by 40, because the temperature change is 40. That comes out to be, on my calculator, minus 8.36 kilojoules. And obviously remember, we're saying it's minus because this reaction is exothermic, which means that it is losing heat, and this is going into the water to make it heat up. Okay, so it's the actual reaction, the burning of the reaction, which is releasing heat. Okay. We are going to now calculate the enthalpy using the same way as we've done before. Okay, so first of all, we used 0.5 grams of methanol. So please, please, please do not get confused between this and the mass of water. Keep them separate. Okay, you use the mass of water to work out the energy released, or the energy change, sorry, and then you use the mass of methanol to help you work out the enthalpy. So that's when you're finding it out for 1 mole. So we're going to do, it was 0.5 grams of methanol. That releases, from the previous part of the question, minus 8.36 kilojoules into the water. So it raises, that's the energy that's went into the water. We need to now work out this for 1 mole. And to work out the mass of 1 mole, we need to use the data book again. So methanol is CH3OH. That's 1 carbon, so that's 12 grams. 1 hydrogen, so that's, 3 hydrogens, which is 1 gram each. 1 oxygen, which is 16 grams. And another wee hydrogen there, which is 1 gram. And that all adds up to 32 grams. So we're trying to work this out now for 1 mole, which is going to be 32 grams. And just like before, this is our N, so our new, our old, and our other side. So that's going to be 32 grams divided by 0.5 times by minus 8.36. actually, don't worry about the minus just now, we'll just add that back in at the end. That means that our answer is going to be 64 times by 8.36, which means that our final answer is going to be minus 535. My writing is not best. Minus 535.04 kilojoules per mole. Now remember that negative is there because this was an exothermic reaction. It made the temperature of the water increase, which means that the chemical reaction itself lost energy. And remember the per mole, because now this is an enthalpy change, you've worked out the energy that would be released if you burned 1 mole. Okay? I'm also going to do this again. I'm going to set up the wee cross multiplication thing for the people that might want that. So we said that 0.5 divided by the 32, okay, that's the two numbers there, would be the same as this 8.36 divided by your x. So your x then, once you've done the steps to cross multiplication, would be 8.36 times 32 divided by 0.5, and that would give you the same answer, minus 535.04 kilojoules per mole. There you go. Now this has an extra wee stage here, and it says, how does your answer compare to the figure in the data booklet? Okay, well, what you'll find out is if you check the data booklet, you'd find out that the actual enthalpy of combustion of methanol is a lot higher. And the reason that this is different and is not the same, or our value that we've calculated is lower, it's going to be because heat could have been lost to the surroundings. I'm going to zoom in for this so it's neater. And also, there could have been incomplete combustion. And that means that the energy formed and released, the energy of the bonds being formed and broken, and the total energy change would be different if it was complete combustion, because the enthalpy of combustion in the data booklet assumes complete combustion, and it assumes that all of the thing would completely combust. So that's why it would be slightly less. So if you're ever asked something about, you're talking about enthalpy of combustion, and you're ever asked why is it not the same, why is it not what you would expect, why is it less, it's going to be because some heat energy is going to be lost to the surroundings, and there's going to be incomplete combustion. Okay.